In the future, many people will live and work in space, and in order to feed them, some may work as orbital farmers, but it may also become how we feed Earthlings too. Farming in space is a popular idea, albeit normally in science fiction it is on some alien planet, but there might be a lot of occasions where it makes more sense to do your farming in orbit. That's mostly for feeding other people in orbiting space stations and visiting spaceships, but as we'll see today, there are some scenarios where farming in space and bringing it down to a planet, even to Earth, might make sense and be economical. We also tend to assume in more distant times that more folks will live in space than on planets. That may be, and if so they need to be fed, and whether you're shipping it down to a planet or to other space habitats, it probably doesn't affect the basic processes and design too much. Though if we imagine settling a planet in another solar system that was more in the Martian temperature zone, we could also imagine an orbital farm that was a very eccentric orbit around that planet to bring it much closer to the Sun for most of its period. Alternatively, you might have a big orbital farm on a cyclar orbit between a planet and its moons that was coming there to pick up raw materials, or between two moons. A cyclar orbital farm moving between Jupiter's volcanic moon Io and icy moon Europa could easily be drawing fuel and raw materials from both moons, and reliably swinging into position of one or the other every 4 days or so, especially with a powered cycler able to give some delta V for pickup and drop-off, and the same would be true of other moons there, albeit with longer timelines. There's a question of getting enough sunlight out at distant planets, but here orbital farms tend to have an advantage. Unlike a planet or moon with an atmosphere, they get all the sunlight reaching their location, either perpetually or except for a small duration in the shadow of that planet or moon. They also don't have to worry about gravity or wind making large mirrors or shades impractical. So we imagine a farm built on Himalaya, one of Jupiter's larger non-Galilean moons, which orbits every 8 months at a distance of 7 million miles from Jupiter, well beyond even its immense and dangerous radiation belt. It could be using that moon for raw materials while using ultra-thin mirrors to concentrate sunlight onto its crops. It would need to concentrate a lot of sunlight, it's down to about 4% of what Earth gets out there, but a thin reflective film, maybe just a few millimeters thick, could be many times larger than the plants and hardware it was illuminating, and yet far less massive and cheaper to build and maintain. This gives us one example of a space farm setup, a large parabolic dish hanging behind the farm like a parachute, reflecting light into it from the sun. Indeed, it might be two farms, since the sun never sets, and you winch the dish a bit to alter where it's sending its light, Farm A or Farm B, or maybe you have a few such dishes and sometimes all three point at one farm, sometimes one on Farm A and the other two at B, sometimes two at A and one at B to replicate noon, night, and in between. What are those farms shaped like though, these deep space varieties? Well, if you want them to have any gravity, you've got to hold to the usual spin gravity approach of rings, cylinders, or a torus hoop. They likely do not need full Earth gravity, as early experiments, while hardly extensive, seem to indicate that most planets don't really need gravity, and where they do, mostly help them line themselves up, so even lunar gravity or less might be just fine. We will hopefully get to experiment on a permanent lunar base inside this decade, but I am reluctant to say that's more likely than not, given the constant pushing back and pruning of Artemis and other previous moon plans. But we obviously won't need to feed lots of people in deep space before we have a permanent moon base, so we can gather data on low gravity and agriculture there. Of course, agriculture isn't just plants, it involves critters on land, sea, and air, and they might need more gravity. It might also turn out that much like lighting and temperature, some flora and fauna might do better in different gravities, in which case you might have a space farm made of either mini rings of different size, or rotational rates, or even a big terrace cone or bowl that's spun and at higher gravity in the wider section, and the habitation section for people, our pets, and maybe our livestock on the outermost ring with full gravity. I do want to emphasize that we'll likely be considering both soil agriculture and aquaponics, not simply hydroponics, or aeroponics, which are both low on mass and thus very attractive for spaceships but less for stationary habitats. Nor can we expect to have any stable ecology, even a shallow ecology of focused farming, without having both plants and animals, including the creepy crawlies, not to mention fungi. We focus on hydroponics for spaceships because it's low mass and they have to exert thrust to move. Orbiting structures, once in place, don't have to worry about mass, and indeed more mass helps limit perturbations and corrections from when ships dock and load or unload mass. More importantly though, more mass can be more shielding, and when it comes to rotating space stations, that shielding is underfoot, so soil is perfect for that role. And when you are using lower gravity, assuming you are, you can get away with more dirt and less structure, as it doesn't need to be as strong to hold up the dirt. That makes them cheaper to build if you need less structure, but you still need the radiation shielding, and micrometeor shielding, and possibly shielding from intentional attack. Some materials work better than others, but good old-fashioned wet soil will serve the role better than mini and let us grow food. You still need to get light in, and you could do that through big windows, but they can also allow radiation in, so it helps to either make them out of something that prevents radiation from getting in, which depending on the material would tend to attenuate desired sunlight too. You might use a meter of water sandwiched between two panes of glass or plastic. Those don't necessarily need to be under rotation themselves, or could be closer to the axis where gravity would be lower, so weight isn't a huge deal. A thick volume of pressurized gas could work too, though we try to avoid needing pressure vessels where we can, and it need not be breathable air, but gas is more absorptive to harmful frequencies and less to good sunlight for plants. We'd also do sandwiched layers, like a glass domed torus that spins right behind a giant thin water tank that does not spin. But we could also use a mirror to bounce in desired wavelengths and little to none of the undesired ones. Any given material is reflective to some frequency, absorptive to others, and transmissive to others, so you can build a good mirror. In fact, it is a lot harder to reflect harmful wavelengths than benign ones. Aluminum is one of the few materials that will reflect ultraviolet. X-rays can usually only be reflected off smooth metallic surfaces at very shallow angles, and we haven't got anything that reflects gamma rays. It would permit so many awesome energy and propulsion technologies. Non-photonic radiation like charged particles isn't going to bounce off your mirror into environments either. This is why we often see mirrors on various space habitat designs, and indeed most of the reason they aren't on more of them is artistic license so as not to crowd out the view of the habitat itself. You can also use a solar-powered magnet to push those charged particles aside, though it helps deploy them a ways out. The default design though is going to be mirrors designed to bounce in the right combination of light to feed your plants and keep the place warm. And if you're in and around Earth, the lighting is about right once you filter out the harmful frequencies. In truth, most plants don't need anything like noontime sunlight, let alone 24/7 light, so we can get away with doing single-layer farming way out to the asteroid belt. Let us imagine the typical ring habitat with its central axis parallel to sunlight, so light passes right through the big middle of the donut. It's open on the top, or transparent, to light reflected in from a big tilted circular mirror that turns on a 24-hour schedule to bring sunlight into the ring, giving it a decent approximation of day and night. Depending on how far you are from the sun, the mirror's surface area needs to be bigger or smaller than the total surface area of the ring's growing area. So you alter the hoop radius, how wide the wheel is, in proportion to the inner radius, how thick the wheel is, or its radius if you thought of it as a cylinder you bent into a hoop. Further out, thicker hoop radius to thinner inner radius. You may have areas of ring that get less light too. We have a lot of optical methods and options for spreading light around. The ceiling, for instance, doesn't have to be a regular window, but if you had sides that got less light, you could grow shade crops there. And you can raise mushrooms or other fungi on the leftover organic matter, or feed it to the critters, or all of the above. But the truth is, you can do a single layer even out in the asteroid belt. Those big parachute-like parabolic reflectors bouncing and concentrating light back to the farm really are not needed till you get to at least the outer asteroid belt, to Jupiter and deeper, and not to work way out in the Kuiper belt. Closer to Earth, and certainly if you're trying to grow food in the Mercury or Venus regions, you are getting too much sunlight and you want to do vertical farming. You presumably bounce light down shafts with mirrors, which then spread that light out to each of their levels. This probably works best if the underside and walls of each level are themselves reflective, so as to help minimize what is getting absorbed as heat, rather than to force power photosynthesis. You can also alter your mirrors, bouncing the sunlight in not to let infrared light in either, to cut down on heat and focus on those wavelengths best suited for photosynthesis, which is mostly red light but some blue and other frequencies, including some ultraviolet light to help minimize mold. It will vary a lot by crop. Some placed nearer the sun, if you are absorbing the infrared right into your mirror instead, then you could let that mirror get quite hot and run a heat engine off it to provide power for other applications. Those other applications needing energy will include things like moving heat and air in the farm, making fertilizer to feed your crops, and processing those crops later, sterilizing soil in the event of disease, pumping and cleaning water, powering robots, and running the overall life support for any human crew, who may live on a farming ring or cylinder, or might live in a smaller secondary habitat. Indeed, if it is a lower gravity ring, they might live in a habitat module hanging down a tether from the ring, swung around like a bolo to enjoy higher gravity, which might be a good place for ships to dock or undock from, since you could lower goods down to them and they could drift in or out at a lower velocity to connect to that faster spinning section and not need to fire any thrusters near the farm, which again is going to be built cheaper and thinner than a normal habitat. Indeed, a secondary habitat for people can be built thicker and safer itself, and farm workers, which is unlikely to involve a lot of manual labor anyway, might wear a light spacesuit with collapsible helmet attached just in case a major blowout occurred, or carry around something like an emergency inflatable bubble, or get followed by a drone that could do that, expand to have a huge mouth, a sphincter they could inflate and swallow the person inside, which somehow sounds kind of terrifying in spite of being an easy life-saving option. As much as we talk about Mars and Titan, Venus and Mercury have a lot going for them as possible areas for space development, and that space is also much easier to get to and from in terms of time, and much easier to get power from, and also rougher on radiation to be fair. It's also probably easier to be feeding people down on mines on Mercury by bringing food in on whatever ships you're taking metal and ore up in, than trying to grow it there. Now, as mentioned, there's a question of who we are feeding with orbital farms, and the initial answer is easy: other people in space. It is insanely expensive to bring food and water to crews from Earth, so as we get more people living, visiting, or working in space, we need to feed them without relying on Earth for all those launches. Now, we're not really interested in modern launch costs here either. At the moment, there's no economic concern for food in space. We only have a few folks up there at a time to grow it, and no space to plant in. So any growth here is more about basic research than any food provided, or additional benefits of air cleaning or psychological comfort. They are a convenient byproduct of that research. Growing food there is more about permanent facilities and periods where we have at least many dozens working up there, and even then the food is more a handy byproduct of the research efforts for learning the basics of ecology off Earth. As time goes on, that need grows as the number of people up there grows, and as our ability to dedicate more effort to other tasks grows there too. For instance, it sure would be nice to be able to tailor spacesuits up in space, ensuring best fits as astronauts might gain or lose weight, and adapting a suit to an individual of varying height and build. But it's going to be a long time before we have enough people up there to allow having a space tailor to be practical and economical. Probably at least 1,000 people. If you can afford to bring 1,000 people to space to work for a year, then you can double that launch weight and cost to bring up enough dehydrated food for them to eat for about a year, same for 1 million people. However, that's a lot like the old agrarian subsistence farming model of basically needing one farmer for every other non-farmer you wanted to support, including young children and the sick or elderly. It's a serious weight around your neck for growth in space when your launch costs are the overwhelming majority of the budget, and half your worker cost is shipping food. In the modern world, depending on how you count it and where you are, that food support figure is somewhere between 1 to 10%, allowing the supermajority of us to do things beside food production, or at least as a part-time job like for myself. For those who didn't know, I live on a farm and do spend a fair amount of time driving my tractor around on it, though not always very skillfully. In fact, it just came back from my brother-in-law's shop for repairs, and when I'm done recording, I'm looking forward to getting my brush hog out to fight all the weeds that sprung up while it was down. Tractors in space are even further ahead in time, though. It's hard to say when the tipping point would occur where it was easier to grow food there than ship it up, even more so when talking about dedicated agricultural facilities. Things get a bit more iffy when we contemplate exporting that food to other off-Earth locations like the Moon, or Mars, or the asteroid belt. But by and large, assuming you're not trying to ship low-storage time items like bananas, it is a lower fuel cost to ship food from Earth orbit to Mars orbit, or an asteroid, than it is to ship it from Earth or Mars. In terms of when they first appear in Earth orbit, we've got 2 points. First is luxury crops, things like fresh fruit, and those might appear relatively early on for space hotels, moon bases, and Aldrin cyclers. The last are mobile space stations that do long trips on elliptical orbits between Earth and Mars, or Earth and the Moon, or any other 2 celestial bodies that either orbit the same primary, like Venus and Earth around the Sun, or where one orbits the other, like the Earth and Moon, or all of Jupiter's Galilean moons. Cyclers are very economical and very slow, and pretty well set up to be growing their own food. Indeed, you might have one on the long trip to Jupiter or Saturn to bring volatiles, water, ammonia, methane, nitrogen, and carbon dioxide, back home wherever the other stop is. That might be Earth or Mars or wherever. People are on them for a long time twiddling their thumbs and eating food, so it makes sense to have either agricultural or manufacturing capacity on them to feed and occupy people making the trips. By and large, you do a lot of recycling too, so some cycler coming back on a multi-year journey to Jupiter or beyond could be converting a lot of their volatiles picked up from out there into edible food that people bought instead of the raw material. There's always a good economy to be had in adding value to your wares if you've got a long time with them. That might move both directions too. Out past the asteroid belt, sunlight is getting pretty sparse for growing plants. You can always concentrate light with mirrors and lenses, but a cycler like that, say one moving between Mars and Jupiter and bringing volatiles to Mars, might grow food for both destinations and not just any passengers and crew it has, or be manufacturing those mirrors for the Jovian moons with elements mined off Phobos or Deimos. Those mirrors might also serve as solar sails for limited propulsion and station keeping. And you are as likely to want to grow food in orbit of Mars or Venus as around Earth, since you have people going to those places and wanting to eat or stock up on food without necessarily paying the extreme cost of bringing up a gravity well. On the other hand, you might bring it down a gravity well, especially if you have an atmosphere to break inside, making the descent basically fuel-free, or some space-to-ground infrastructure like orbital rings, space elevators, or space towers. This takes us to the notion that we might be wanting to feed a planet below, and maybe Earth itself. We see examples in fiction of this, but even these are often unrealistic or contrived. We have a neat example of it on the planet Grayson in David Weber's Honor Harrington sci-fi novels, where the planet is basically a poisonous wasteland, and they have cheap anti-gravity technology for getting to and from space. But even here you wonder why they don't just build greenhouses, and you seal the floor too, not just the ceiling and sky, which we would do for domes on any new planet where there's no native soil and you have to make it out of regolith that probably needs processing to lower toxins first. Indeed, in later novels in that setting, they do start building giant greenhouse domes on Grayson itself. I'd imagine the author realized that made more sense at some point, and Weber does generally write very good sci-fi from a technical standpoint too. Great set of novels, especially if you like military sci-fi. From a realistic perspective, as long as we're considering a population lower than currently, or at least not several times larger, we would have no reason to bring food down from orbit, just sunlight, and indeed might feed quarter plants by bouncing more sunlight in from big thin mirrors in orbit. We use about a third of the planet's land area for agriculture in some fashion, but realistically, most of this usage is very inefficient, calorie-wise, compared to what we are capable of, and that doesn't even include the deep oceans, which are basically wastelands from a lack of nutrient and most of our planet's surface, but also easily turned into farms themselves, at least more easily than building orbital farms. Building farms in orbit is one thing, keeping them running forever is another. That's where automation comes in, and it's the focus of my new Nebula exclusive episode, Autonomous Space Industry, when AI and robots run the economy. We'll explore how intelligent, self-replicating industry could terraform asteroids, build greenhouses in orbit, and make humanity's food supply truly cosmic. While you're on Nebula, check out Scav, the new original docu-series from Wendover Films. Every year, a 20-page scavenger hunt list throws the University of Chicago into 4 days of sleep-deprived brilliance as 3 top teams race to compete the most ridiculous and inventive challenges imaginable. It's creative chaos at its finest. Nebula is home to many thoughtful new originals from top creators, along with dozens of SFA exclusive episodes, extended editions, and other bonus content. You can find SCAV, Autonomous Space Industry, and every SFA episode early and ad-free at go.nebula.tv/IsaacArthur. Get a lifetime membership, normally $500 for just $300, and unlock everything forever. Or get an annual plan for 40% off, $36 a year. That's 12 months for the price of 7. Scan the QR code or click the link below to start watching now. We could probably feed the entire current planetary population on less than half that land without any major changes to diet, and that's without space-saving options like greenhousing over areas, particularly areas that are low on rainfall or temperature. Those are not economical while we still have plenty of land and not a lot of people, but they become more economical when that starts running out and remain so long before farming in space for import is likely to be viable. Though do keep in mind that you don't have to spend fuel to bring things down from orbit, and even if you were importing 1 ton per person per year, call it 10 billion tons a year, it would take longer than this planet would be around to raise Earth's mass even 1%, so you don't really have a mass limitation. You could conceivably decide a relatively roboticized orbital farming and mining sector could be supplying Earth, dropping food down in easily recyclable pods or down tether trains from orbital rings, while leaving Earth free from farming and mining efforts. And you could always export your waste back to space. Or you might just have so many people on Earth that you need the space for a living area and can't devote enough energy to grow food on Earth. After all, as we discussed before in the context of Eucomenopolis's planet-wide cities, it takes more energy to light crops than basically every other thing people need to support themselves, all of which leaves as waste heat, which becomes your maximum constraint on population. Every person needs so much energy, and emits that as waste heat, and Earth has a maximum heat it can radiate off. If you can cut that per capita budget down to 1/10 by cutting out local food production, doing that in orbital farms, then you can support 10 times the people. Whether or not you want to is another story, but Earth is likely to be viewed as ultra-valuable real estate in a future in which most people don't live on Earth. It also might not be a matter of preference. As we discuss in episodes like Hive Worlds, there is no reason why a planet-wide city has to be disgustingly dystopian. It could be quite the garden park, but that depends a lot on how you're doing your growth and managing things in general. I would expect it to be several centuries before the majority of humanity lives off Earth, and even longer before it mostly lives away from Earth rather than in the cislunar neighborhood. But predicting how quick we'll grow and where tends to be a fairly murky process. In the long term, I tend to assume humanity's future thousands of years from now includes many trillions of people living nowhere near Earth, but how that grows in more mid-term context is very dependent on tons of factors we cannot foresee, including how we do on-food production technologies, life extension technologies, fertility medication, automation, energy abundance, and a million psychological and sociological factors that will vary by nation and generation. There's a lot of debate on if Earth's population is rising, falling, or settling out to a stable number. To the best of my knowledge, it has risen every single year during my lifetime or anyone currently alive's lifetime. But in prior times it often did stabilize or go through quick growth or loss cycles. A lot of folks predict it will settle somewhere around 9 to 10 billion by the end of the century. I tend to guess a bit higher, but not by tons. Others think it might even decline, and population projections are notoriously inaccurate and reductionist. Simple form, technology makes it easier to stay alive to have kids, to let people have kids, and to keep those kids alive, but also makes it easier to not have kids when you don't want them. Tech increases capability, culture and lifestyle control desire. Given that culture is not homogeneous nor unchanging, I tend to raise an eyebrow at some of the sweeping generalizations folks often employ to pronounce how population numbers must go. My own stance is that biology inclines us to growth and technology makes it easier, and that civilization is composed of people with eyes and brains who do not want to go extinct or live in a Malthusian nightmare, and thus public sentiment will generally tend to tilt toward comfortable growth. Which is to say, if you've got plenty of resources, and feel like growing more isn't going to reduce standards of living, or wreck the environment you're in, both ecologically and in a community sense, then growth is where you're headed. Most of our growth these days is not in developed countries, indeed many are in population decline, especially without including immigration. From this, folks often forecast that as we develop our world, population growth will decline in those areas too, which is reasonable, but we also need to keep in mind that we have a lot of Malthusian baggage impacting our thinking too. As the developed world entered the industrial era and modern age, we got way better at farming with less manpower, and indeed less land, and folks migrated to cities, which were often filthy, not that the farms were not, but crowded and smog-choked too. We have a lot of background culture from that era that tends to make us think having tons of kids is bad, that it robs people of a chance to do something other than just being a parent, while resulting in eventual mass starvation as we deforest the planet and eventually settle into a slow death of crowded cities of gaunt, sad people living on algae and Soylent Green until eventually we die, leaving a murdered planet behind us. When you grow up on that diet of dread, it tends to make you a bit less likely to have kids or encourage others to have more. As a techno-optimist, I tend to feel more people as more brains solving problems, so long as they have a surplus of resources to use to solve those problems, and thus like modest growth and tend to figure we'll have cleaner cities and need less farmland per person, and that these do not have to look like dystopian nightmares. One thing about having a show that comes out every Thursday, or at least has since the second season, and now we're nearing the end of the 11th season, is that we always end up with an episode on Thanksgiving. Sometimes we do holiday-themed episodes when one falls on a Thursday, but rarely for Thanksgiving. Still, it's hard to imagine a topic more fitting. The days are growing shorter here in the Northern Hemisphere, the seasons can feel a bit bleak, and Thanksgiving is that reminder of how much we had to be grateful for. We live in an era of abundance after so many generations of hardship. Looking back at the past helps us appreciate that, but looking forward to the future can be just as important, to glimpse what we might yet achieve. I do not believe the world literally changes depending on whether you see the cup half full or half empty. It's still the same cup. But your perspective matters enormously. Believing you have some control over your life is not only empowering, but well documented to improve outcomes. This season can be a depressing one, and Thanksgiving may either lift your spirits or leave you feeling worse. I hope it is the former. Either way, it's also a reminder that the year ahead can be better, and that even if the world sometimes seems to drift toward dystopia, there's always a chance to steer it elsewhere. You can help shape that outcome. And if we're wrong, if all our efforts are no more than flapping our arms while tumbling off a cliff, well, at least it keeps us busy on the way down. And maybe, just maybe, we learn to fly. It's a bit of a tangent and one we've discussed more, both in utopian and dystopian light, and points in between, in our episode Hive Worlds, Hungry Aliens, Space Freighters, and Agri Worlds, which this episode forms a loose quintet with on the topic of how we feed mega-civilizations, which means we covered some points in those that we will skip today for brevity. Though of course we try to keep every episode self-contained so there's some repetition too. I think a lot of our bigger space habitats, like O'Neill cylinders or the Stanford Torus, while often shown with farms inside them, probably would be more dedicated to living space, whether it be suburban setups, urban, or even gardens and forest parks. I think most of your food is going to get grown in ancillary facilities near the habitat, and probably all bound together on a web of tethers for fast transit, power transfer, and high bandwidth communication. Do we end up growing food for Earth? Not anytime soon, but I do tend to think in a growing human civilization off Earth, that our pale blue dot becomes the most valuable gem in our realm, as it already is, but now it's a gem in isolation. Folks talk about moving off Earth to help restore it to its pristine state, and that may happen, but I think more likely we would have nature preserves in space and turn Earth more into the capital of the solar system and the center of travel for friendly systems nearby. So if you can farm food off in space for less than you can buy, maintain, and rent out human residential spaces, workspace, and thought spaces, then I think you end up doing just that. Earth's hill sphere is the region it gravitationally dominates, so is where we would tend to locate things meant to be attached to Earth, like the orbital farms feeding it, as this is where things can be in stable orbit around Earth, and also within only a few seconds of communication and days of travel. Attached might not be metaphorical or gravitational either, more on that in a moment. Elliptical orbits can go out beyond this, as can anything that's in our orbital path, like our Lagrange points with the Sun, or anything between us and them. That Hill sphere stretches out 235 times wider than Earth and gets 55,000 times the sunlight, which is quite sufficient to supply energy and food to Earth in a way that cuts down the amount of heat Earth needs to get rid of. That's why we like power beaming and orbital farming for eucomonopolist planets, as it means instead of needing megawatts of sunlight and heat waste per person for the food they need, we might only need low kilowatts. As an example, I said earlier we use about a third of the surface land of Earth for agriculture in some fashion, and that amounts to about 10% of the sunlight reaching Earth, and that works out to be a couple megawatts per person of sunlight constantly. We could do a lot better by greenhouse farming and bouncing away infrared light from the planet before it arrives, while bouncing in more photosynthetic wavelengths. But getting under 10 kilowatts a person is iffy, and we could probably do food and power production off Earth and keep that down to the kilowatt range per person, allowing something like 100 trillion people on Earth in relative comfort. Space is not an issue. As we discussed before, even that immense population density is well short of what a planet of skyscrapers would support, with more space per capita than the average for an entire upper middle class modern household would have. See the Hive Worlds episode for that, but it already means that the Hill sphere alone could support the agricultural and power generation, along with most manufacturing, that an urbanized planet would need. We call this a planetary swarm, as it's basically a mini Dyson sphere around a planet, and for those thinking in Kardashev scales, where a fully developed planet is K1 and a Dyson swarm of a whole star is K2, a full planet swarm is going to be K1.4 to 1.5, amusingly quite a match for most galactic empires in science fiction. As we discussed in that Hive Worlds episode and our interplanetary infrastructure episode, there are ways to physically connect yourself down on a planet to your Lagrange points and to a large ring or torus encompassing your orbital path. So you could actually take a train from Earth around the Sun and back to Earth if you wanted and were big enough. Such trains can be moving food and water and other cargo too. And you could instead urbanize a planet, suburbanize your planet's swarm, and grow your food in that immense ring or torus around the star that your planet orbits through. We call this a Terran ring, though it is more of a torus or ring-shaped ribbon, and depending on its diameter, thin ring or wide hoop, it could be anywhere from K1.5 up to K1.7. Each decimal on the Kardashev scale is 10 times more people, so if you're supporting 100 trillion as a K1.4, you can support 100 quadrillion as a 1.7. And you could build it up like a series of ring worlds if you like, but that's a different topic for a different day. So too, getting resources for all these things, be it the structural material or the soil, air and water, and fertilizer or nutrients, are topics we looked at more in episodes like asteroid mining, comet mining, atmospheric mining, and that Space Freighters episode, when it comes to bringing them in economically. For now, that's Orbital Farming, eventually bringing you the drink and snack you'll need to watch this and future episodes.